In the field of physics, the word distribution is thrown around a lot in statistical mechanics, the field governed by probabilities. A distribution is simply a way of representing a certain population of, in this case, particles, atoms, molecules, that are likely to be at a given state, a given amount of energy, a given state within a system or ensemble. And the three types of distributions looked at are the Maxwell-Boltzmann distribution, the only classical example, and then the two quantum examples, which are Bose-Einstein and Fermi-Dirac distributions. Each one has its own area of expertise and also has various nuances that come into play for deciding which distribution is most appropriate. And as a general breakdown to compare each one, just going from left to right, for the classical case, this is dealing with particles which are identical to one another. However, they are distinguishable from one another. In this case, their wave functions will not overlap with one another. In both quantum cases, these are dealing with systems of particles which are identical but are not indistinguishable from one another. Therefore, their wave functions can and do overlap. Bose-Einstein distributions are for particles with whole integer spins, 1, 2, 3, 4, etc. And then Fermi-Dirac distributions are for particles with half integer spins, from 1/2, 3/2, 5/2, and onward. Maxwell-Boltzmann distributions, they are wonderfully well suited for modeling ideal gases in the macroscopic scale. Now, Bose-Einstein distributions are for bosons specifically. Bosons can include photons, particles of light, but also collections of fermions that when their half integer spins are added together, such as in the case of some atoms, the total becomes a whole integer nuclear spin, such as the case of the helium-4 atom or the helium-4 nuclei, where the half integer spin of 2 protons, 2 neutrons, and 2 electrons all come together to equal a whole integer spin. Getting into what fermions are, those are what are covered specifically by Fermi-Dirac distributions. Fermions include all the subatomic particles or all the subatomic particles that build atoms or elsewhere, such as electrons, protons, and neutrons, even positrons as well. All of these have half integer spins and can be described through Fermi-Dirac distributions. When on the quantum scale, with Maxwell-Boltzmann distributions, multiple particles can occupy the same state, the same collection of properties. The same is true for Bose-Einstein distributions. However, for Fermi-Dirac distributions, these have to obey the Pauli exclusion principle, which states that only one particle can ever exist in a specific state. Fermi-Dirac distributions forbid multiple particles coalescing into the same state, whereas that is possible for bosons and for particles on the classical scale. taking into account the distributions, what we see here is simply n sub s. That's just representing the average population of, or the average number of particles for a given population that are in a certain state, sub s. Now, this beta factor, the thermodynamic temperature, thermodynamic beta, that is simply the reciprocal of the product of the Boltzmann constant and temperature. So 1 over kBT. Epsilon, or E as it's written elsewhere, that is the energy. Epsilon sub s being the energy in a given state compared to a quantum state S compared to a quantum state R. And mu is the chemical potential, which shows up in the quantum realm. For Bose-Einstein distributions and Fermi-Dirac distributions, the interesting difference is simply in the formula. The difference of whether the exponential in the denominator is being subtracted by 1 or being added by 1. Where in the case of Bose-Einstein distributions, it's subtracting by 1, and for Fermi-Dirac, it's the addition of 1. Where this seems like a slight change, it has a wide range of importance for whether we're talking about bosons or fermions. But what's very fascinating is that in both the Bose-Einstein distribution and the Fermi-Dirac distribution, as long as the number of microstates or the number of states possible for a system is much larger than the actual number of particles, then both of these will actually drop into the Maxwell-Boltzmann distribution, as in the quantum scale breaking into the being able to coalesce into the classical example.